So good morning. My name is Rolland Dudemaine. I work for TrustInSoft, and I'm going to talk about using Rust in the critical industry. So let's see how many of those you recognize. Obviously, in the middle, you find N Group, Huawei. Then top left, you have Google Pixels, phones, Ford cars, rockets, and from Ariane and Airbus planes. Can you think of 3 common points that they have? First point is that they do mission critical things. Mission critical can mean life critical. It can mean, well, the cars, for example. It can mean money critical for the phones. It can mean for the rockets that you can't fail. If you launch and explode, obviously that's money. So mission critical. And the second one is that they all use Rust, or they've started to use Rust. And they all use Rust in the critical areas. So they need to do it right. And the third one is that actually they work with us as well. Why do they work with us? They work with us to find what remains of the bug. So what I'm going to talk in this presentation is how safe and secure Rust is. Why do people actually switch to Rust? Is because they find that using that language actually improves everything. And they're right, but does it actually solve the general problem? It does not. Actually, that's another thing. You know the crab, Ferris? The crab represents everything that's good about Rust. Do you know the little guy below? Some number of people actually don't. That's coral. Coral actually represents everything that's unsafe. Everything that actually is left to go. So in the future situation, Coral should have a smaller and smaller and smaller role if things go right. So again, I'm going to say good things about Rust, but I'm going to criticize it as well, because you can't be production ready if you don't know the limitation of everything you're using. So, okay, yes. So when you look at Rust, the initial decisions actually didn't start from scratch. It was not just, let's do something new that's totally different. There was some acquisition, there was some reuse and lessons learned from the past. And actually this is great because that means that it's very modular. It's already actually more than 10 years old. So it took some time to reach a point of maturity, but it's actually really truly making things harder to write bad code. I work with a lot of people in the safety domain, in the regulated industry, and they tell me, especially safety managers, that when people were coding in C, they had difficulties to make engineers work in a reliable way, to follow good practice, to follow good coding standards, to test correctly. With Rust, actually, it moves you in that direction. You have to test. You have to use good practices. There's also an integrated test framework. There's also integrated documentation. You also have production tools. And all of that should already be known to you. Because I have Rust positive people here. What is less obvious, though, is that over the course of making design decisions for implementing Rust, there are a few things that have been decided to actually make sure that everything is understood, correctly decided. On the good side, for example, the Rust code that is generated is inherently memory safe. But memory safe does not mean that everything is checked at compilation time and there is nothing left at runtime. There was also a decision that when you have to decide between speed and control, well, there's no compromise. It's going to be always both, but everything, well, there's some level of static analysis of the code you can't do at build time. And when the compiler can't do it at build time in a reasonable time, then it will instrument the code to actually do the check at runtime. So I've been writing C code for more than 20 years, and when I learned Rust, I started to write some Rust lines, and I didn't know the Rust modern patterns. I'm a convert. So these are one among the first lines of code that I wrote, and that crashed. Well, it didn't crash, it panicked. Meaning the code, the compiler did not check that something would come wrong in that code. It would decide that it cannot decide at compilation time, and then it instrumented the code. It generated runtime checks, and the runtime check fails. In case you can't see it, actually, I'm passing a dynamic array by reference here at the bottom, and that array is 10 elements and goes from 0 to 10, and then the top has a loop that goes from 1 to 10 included. And of course, that means that there's an off by 1 error, and then it will go and do a buffer overflow. So the good thing is that the code was actually not corrupting data. It did a panic before there was a data corruption. But if you run in an airplane, if you run critical code in a car, that still leads into a panic. You can't crash, you can't stop running in a car. That's impossible. You have to figure out, you have to avoid panic. Yet, that code does not build with any warning. So that's really important. You have to realize that because you use Rust, it moves you in the right direction. It will create more robust code, but it will not solve and guarantee that everything is fine. It will only actually allow you to control what you're doing. So that means you still need something to figure out how it would panic. It would not panic, sorry, after deployment. That can mean good practices. That can mean tools. Mary is there to help you for doing initial dynamic analysis. TrustInSoft takes another approach. And so that's that. Where you know what you're doing, you can actually call unsafe. Unsafe is telling the compiler, I know what I'm doing, trust me. Of course, you have to be very careful, because if you do that, then you're on your own. If you actually did something bad, that's your decision. But sometimes you need to do it. And of course, don't do it. Do not use unsafe until you really have to. Good reasons for unsafe is when you actually work with external code that is not made in Rust, because then the Rust compiler cannot guarantee anything about that code, so you have to tell the Rust compiler, I know what I'm doing, I'm calling something from the outside. Good reason. When you access the hardware, likewise, you're accessing something that the Rust compiler can't even evaluate. It's hardware, it's external, unsafe. And then sometimes, in very, very, very corner cases, you can actually use unsafe to explain that the compiler that you're doing, you know what you're doing, and then there's that. All right, so Rust is modular, Rust is reliable, Rust, you can still tell the compiler that you know what you're doing. That's great. And another feature of Rust is the fact that you can use cargo to import crates, to import code that other people already wrote. This is actually fantastic, because you don't start from scratch. You don't start from zero. You can benefit from everything else that the community did. And again, when you do software that has to run in general, that's great. You can go much, much faster. When you are creating code that must absolutely not fail, or people die, or billions of whatever currency, billions of yuan actually go away, that's actually a little more critical. You need to know what you're doing. You need to make sure that you only use tested code, verified code. And the beauty of open source is you can reuse the part of open source that you have to realize is that when you use code, you become responsible for that code. And so I don't know if you know the XKCD reference on the left there, but basically when you start to reuse something, but there is a little guy, a little crate somewhere that someone is maintaining and that is not actually verified well, and if that one has a bug, everything falls apart. So again, be sure of what you're doing and be sure that you're using the right crates and the right dependencies. And so what we see in mission critical software is that either people will not import open source code, they will recreate their own services directly, or they will basically take versions of crates that they know, then they will use cargo version and create a cargo.lock to be able to lock the crates in the versions that they know are working. And for some of the customers I've been working with, they actually create additional tests. They test what they use again to go to the end of it. Well, so that's important. Again, it's not criticism of Rust. It's just saying, now you know what you're doing. So, is there actually still a remaining security problem? Well, when you were in the world of other languages in the embedded, like if you use C and C++, C and C++ still have actually a lot of undefined behaviors. Memory safety was an issue, or still is an issue. In Rust, you limit the issue or you remove the issue, so there's no security issue anymore. Well, sorry, there is. RustSec is a project that's actually really important, really interesting, that tries to reference all the security and vulnerabilities. There are some debates whether the source and the list is actually reliable and whether what the work they're doing, but actually it's still a very useful reference to look at what's going on. And over the years, more and more security issues, potential security issues are found. So that means that security still remains a problem. Is it a lower problem than in other languages? Yes, no question. Does the security topic disappear? No, it remains. So you still need to know what you're doing. So that means that there's a reliability problem that lowers, but still is there. There's a safety. Thank you. Reliability is important. So basically reliability is still a topic, safety is still a topic, security is still a topic. It's actually an easier topic than before, or a smaller topic than before, but it does remain. A little word on TrustInSoft, the company I work for. We're a French company. We have offices all around the world, including in China. My colleague over from Wuhan is here. The founders of TrustInSoft actually worked on the open source Framacy software. Framacy is basically it's a formal methods engine. The open source version is focused on making a proof of software, and it mostly works for the C language. The thing about formal proof is usually you have to provide your code, and you have to provide a specification in an additional language, and then it's basically an engine to match the specification with your code. The creators of TrustInSoft decided that maybe you can already take only the code, because nobody wants to write the specification, nobody has the time or money to write it. You can just take the code and then use some particular engine, abstract interpretation engine, to look through the code and figure out if already some errors. And basically, so what's interesting is then TrustInSoft can actually take your code and analyze it in the C, C++, and Rust language. And our tool is already qualified for use in automotive, in aerospace and defense, well, we have some of those customers. Concretely, again, so the technology behind it is called abstract interpretation. And basically, it's a very fast graph traversal. It takes the code, starts from the entry point with the values of the data that you gave, and then will simulate the code to understand how the data could go wrong over the statement, over the execution of your software. It's kind of a very advanced simulator also, because it will take into account the architecture you're running on. If you're running on RISC-V 32-bit or ARM 64-bit or Intel, then it will consider the architecture specifics. And what's actually pretty unique with it is that you can combine Rust and C code together. So if you have Rust code that calls into an external library in C, you can provide both sources, and then the analyzer will be able to understand how the value, how the data goes through into the C code and back, and vice versa. If C code would call Rust, then we can analyze that as well together. Well, of course, it's an engine, so it will create some, it will do the analysis and create some report, and we also have in the middle some kind of debugger. Because another unique point about it is it's not like MIRI, which will consider the single inputs that you give. Because it's abstract, you can actually give ranges of data as input. In the best case, the tool can understand what would happen for any value in the application. So when the tool tells you that there is no issue and you gave all the possible inputs as in your interface, then that's a proof that there is nothing left to find, which is actually pretty powerful. So concretely on Rust, what do we do? I mean, the compiler already does a lot, so what do we do? In safe Rust, the analyzer will find paths that lead to panic. So exactly the problem that is left to find. In safe Rust, the compiler gives you already a lot of information to be able to create robust code. But again, that's what I showed earlier. Sometimes it will instrument the code to do checks at runtime. Our analyzer will allow you to understand data overflow issues that are actually defined, and also it will allow you to find paths that lead to a panic by doing that simulated execution. In unsafe Rust, it also does that, but it will also point out undefined behaviors, which still exist in the unsafe area. On top of that, it can point to you some coding issues. And when I mention coding issues, it's not like Clippy, which are mostly syntax issues. I'm talking about behavior issues. So for example, things that most people ignored in the C language are signed overflows. So when you do calculations and it would go around in your signed integer, this is something that is defined in Rust, but typically this is something that should never happen. And our tool can report that based on an actual simulation of what would happen if you run the code with these values. And then when the unsafe Rust actually calls an external library, typically extern-C, then again, the analyzer will go through the Rust code and then go through the C code across, considering what the inputs from the Rust world were into that, and then go back. So it can point issues in the C code that come from the Rust values, and it can point to Rust code coming from the result of the C calculation. And of course, it finds undefined behaviors in the C and C++ language, and that was the original intention of the tool. So that combination is pretty important. And on customer code, we have found interesting critical bugs that neither C tools or Rust tools could find. And the combination led to problems. What does it look like? Well, it's a command line tool, so typically you run it as part of your CI. And then you get a nice report. On the left side here, you find an example of an alarm. There's a division by 0, and you can see at the bottom that the value, the resulting value in some calculation that's a Caesar algorithm is leading into a possibility of an output that goes from 0 to 10,922. And the problem is that includes 0. So there was a risk of division by 0 in this case. And on the right side, you see an example of a code coverage report. Because the analyzer does not just do syntax checking, but it really does a simulated execution, the tool remembers each state of the execution. It's kind of like a perfect trace. And because we have the complete trace of the execution, then we can also output a code coverage report. And because that code coverage is actually qualified, that means you can do your unit testing, maybe with cargo test, for example, and create code coverage, and then give that to your certification authority for verification, for safety or for security. Concrete case, we work with N-group, and so that's an analysis. You see about many functions and many statements, because the Asterinas OS is a big project, and this is only a tiny subset of the Asterinas OS from N-group. And that's an example of an error which we still have to confirm. I don't think it's a real one, but that's an example of what we get. Well, you can see that the report actually shows Rust code. So again, because in this case, this is a Rust-only analysis, but what's interesting is that Asterinas uses modern construct, and we're developing our tool still as we speak. It is, we expect the first release for Rust in October. So still you can do code coverage on the tool, and you can do the analysis on the tool using everything that's advanced in Rust. So that includes match, that includes closures, which is particularly difficult to analyze and to understand using static analyzers. In our tool, that's working, and of course we're adding features every day. But the point is, you can use it concretely on code now. I want to take a different perspective, a completely different perspective, because so far everything I talked to can be understood, was targeting kind of the core engineers that develops. But when you step back, when you do a critical project, usually you have to do requirements, and then basically in regulated industries. You write requirements, you do your coding, and then you verify that everything was fine. It's a classical V model. But in fact, there's not one V model. There are 3 V models, at least, because the safety assessment also does the same, and the security assessment also does the same. There are also requirements like this to follow. Rust actually allows the simplification, basically it allows to reduce the risk that when you do the verification, especially when you go back to system verification, you will find critical bugs. But it still can happen. And using TrustInSoft Analyzer on C, C++, Rust, and combination, we actually pull that even further. At the developer seat, you can find more bugs earlier, and that means those hard bugs that remain at the end do not happen. So the verification and the general cost of developing goes lower. Everything is a little bit better in that way. All right. Come on. Working? Not working? Yes. So, I mean, that's the last slide of my presentation. When you think and you look at the story of how to build and develop and test and verify your applications in production, well, first of all, take a stable tool chain. You can work with upstream, of course, of the main stable one. There are some companies who can provide you with a supported stable version, qualified version, safety qualified version, like Ferrosystem, for example, with Ferrocene. You can do your unit testing with cargo test or whatever test you want. You can attach it to special analyzers like TrustInSoft analyzer if you want to. You can do traceability of requirements. Nothing has changed. I mean, that's still the case as with any source. You can make sure that you have good coding standards and you write reliable code. Clippy will help. TrustInSoft Analyzer will help. And then code coverage, you can do it with LLVM and TIS-Analyzer. And for cybersecurity, well, TrustInSoft Analyzer will help as well. That's the end of my presentation. Thank you.